better at tasks through experience is part of being human. When we're born, we know almost nothing and can do almost nothing for ourselves. But soon, we're learning and becoming more capable every day. But did you know that computers can do the same? Machine learning brings together statistics and computer science to enable computers to learn how to do a given task without being programmed to do so. Just as your brain uses experience to improve at a task, so can computers. Say you need a computer that can tell the difference between a picture of a dog and a picture of a cat. You could begin by feeding it images and telling it, this one's a dog, that one's a cat. A computer programmed to learn will seek statistical patterns within the data that will enable it to recognise a cat or a dog in the future. It might figure out, on its own, that cats have shorter noses and that dogs come in a larger variety of sizes, and then represent that information numerically, organising it in space. But, crucially, it's the computer, not the programmer, that identifies those patterns and establishes the algorithm by which future data will be sorted. One example of a simple yet highly effective algorithm is to find the optimal line separating cats from dogs. When the computer sees a new picture, it checks which side of the line it falls on and then says either cat or dog. But of course there can be mistakes.
SVMs, or support vector machines, are some of the simplest and arguably the most elegant methods for classification. Each object we want to classify is represented as a point in an n-dimensional space, and the coordinates of this point are usually called features. SVMs perform the classification task by drawing a hyperplane, that is, a line in 2D or a plane in 3D, in such a way that all points of one category are on one side of the hyperplane and all points of the other category are on the other side. And while there could be multiple such hyperplanes, SVM tries to find the one that best separates the two categories, in the sense that it maximizes the distance to points in either category. This distance is called the margin, and the points that fall exactly on the margin are called the supporting vectors. To find this hyperplane in the first place, SVM requires a training set, or a set of points that are already labeled with the correct category. This is why SVM is said to be a supervised learning algorithm. In the background, SVM solves a convex optimization problem that maximizes this margin, and where the constraints say that points of each category should be on the correct side of the hyperplane. Using SVM can be as simple as loading a Python library, preparing your training data, feeding it to the fit function, and calling predict to assign the correct category to a new object. Given some information summarized in an independent variable x, for example the height of a person, predict the value of another dependent variable y, like their weight. Usually we have a training dataset, that is a table that contains values for both x and y that we want to use to infer what the function g should be. We can then use that learned function g to predict the values y for new values of x not seen in training. Finding the right function g is called regression. And the easiest way to do this is to assume that this function g is a linear function, hence the name linear regression. Here alpha is the slope of this line and beta is the intercept. The simplicity of linear regression makes it really attractive. We're only dealing with linear functions here, so no complicated neural networks involved. If you are faced with a prediction problem, linear regression should really be the first thing that you try. To do linear regression, we just need to pick the alpha and beta that makes this line fit the data as much as possible. One way to quantify the fit of a line to a bunch of data points is to consider where the point in the training dataset is and where it should be according to this line, take the square of the difference, and then take the sum over all data points. To find the alpha and beta that make this quantity as small as possible, let's take the gradient, set it to 0, and solve for alpha and beta. In practice, you don't have to do this derivation by hand. If you feel more sophisticated, you can fire up Python, import scikit-learn, declare a linear regression model and feed it the training data, and call the fit function. To get predictions, you can just use the function predict.
The more data the computer receives, the more finely tuned its algorithm becomes, and the more accurate it can be in its predictions. Machine learning is already widely applied. It's the technology behind facial recognition, text and speech recognition, spam filters on your inbox, online shopping or viewing recommendations, credit card fraud detection, and so much more. At the University of Oxford, machine learning researchers are combining statistics and computer science to build algorithms that can solve more complex problems more efficiently, using less computing power. From medical diagnoses to social media, the potential of machine learning to transform our world is truly mind-blowing.